Hello, everyone. Thank you for joining our webinar. I'm Jeremy White. I'm a hydrogeologist at INTERA, and I'm joined by my friend and colleague, Melanie Beck, who's going to lead the discussion today and presentation on some work we've recently done for the North Dakota Department of Water Resources. This is one small aspect of a much larger project where we were developing predictive groundwater models for the Department of Water Resources to aid in resource management. And what Melanie's going to talk about is constrained multi-objective optimization, which in my mind, there is no better way to maximize the utility of a groundwater model for decision support than with multi-objective optimization. So a little bit of housekeeping. We're going to take questions and comments in the chat, and we'll try to work through those as we're going along. The presentation will be recorded and shared with everyone who signed up, whether you're here or not, after today's presentation. And I think that's about it. And with that, I'll turn it over to Melanie.
Okay, thanks, Jeremy. So my talk today is called From Models to Decisions, Applying Multi-Objective Optimization to Support Groundwater Resource Management. Before I jump in, I just want to thank my co-authors. So Jeremy White, who you just heard from and is on the call today, and then Jay with the North Dakota Department of Water Resources. Jay manages this site for them, this aquifer we're going to be focusing on, and he's got modeling brain and was a huge help in setting up this model correctly and also helping with this optimization problem. So his results wouldn't be nearly as cool if it wasn't for him. All right, so with that, I'll go ahead and jump right in. All right, so on the agenda for my talk today, I'll spend a little time setting up the background for the site. And then I'll talk about the ModFlow 6 model we built for this aquifer, what our modeling objectives were, how we built the model to meet those objectives, and then our calibration setup and results. Then I'll spend the majority of the talk focusing on optimization. I'll give sort of a general overview on optimization problems, how we set up our objectives for this problem, and then our results. And then I'll spend a little time talking about the reliability of the solution and where we plan to go with the reliability analysis. And then I will summarize and go over any future work we have planned. Okay. So a little background on the site. So this is the Elk Valley Aquifer. It's located in eastern North Dakota on the west flank of the Red River Valley. I'm showing a cross-section here from west to east across the widest part of the aquifer. So you can see a steep grade and topography as you go from west to east. That's heading towards the center of that Red River Valley. The aquifer thickens from west to east. It's not very thick, on average about 50 feet and at most 100 feet. It has a high degree of connectivity with the surface water features being alluvial. So I'm showing all of these major rivers and streams that run through the aquifer area here on this plan view. Particularly the Turtle River, the North and South Branch run right through the center of the aquifer, heading east where it eventually meets up with the Red River and that Red River Valley. Groundwater use has been increasing over time for this aquifer. So currently about 12,000 to 15,000 acre feet per year being withdrawn. Primarily, the increase has been related to irrigation, but there's also been an increase in rural water use as well. I want to give a little background on the water rights framework for North Dakota. I'm going to focus on these two types of permit because they're important to the analysis. So prior appropriation versus deferred permits. So prior appropriation, these are active permits. So people who have approved usage of the water in the aquifer. Senior rights does apply to prior appropriations. So in times of shortage, juniors get curtailed first. In this case, a senior is just someone who's held their permit for longer. Deferred permits. These are permit requests where administrative review is complete, but there's insufficient hydrologic information to suggest, what the impacts would be on prior appropriators, the resource, or public interest. So there's really just not enough information on whether or not the requested water use would impact the system as a whole. So in this case, these are held pending until we get additional hydrologic information or changes in water use. You never know when a prior appropriator might decide that they don't need their permit anymore. So for Elk Valley Aquifer, there are currently 49 deferred permits across 117 points of diversion, or POD. In this case, a point of diversion just represents the area where the groundwater would be withdrawn from. So I'm showing a map here of all of these points of diversion associated with these 49 deferred permits. Those are the blue polygons. I'm also showing the management zones for this aquifer, so how deferred permits are managed by zone. These are split up by the north and the south branch of the Turtle River, assumed to be hydraulically independent from one another. And the idea being that permits are handled as they come in, by date, prioritized by date. And so for each one of these zones, they can be managed independently. So if a new permit request comes in the south zone, it doesn't necessarily have to wait for an approval in the middle management zone because it can be handled separately. The total volume requested across all of these permits is about 36,000 acre feet per year, so more than double the existing water use. So there's a high demand right now for this aquifer. And permit activation is on hold due to concerns with water availability and drought resilience. And so that's really the main problem in question that is set up for this aquifer, which we built a ModFlow 6 model to try to address these questions. So our main model objectives were decision support, determine how many, if any, deferred permits can be activated under existing conditions. And then with those active permits, what can the prior appropriators expect as impacts to them? And then what could be the possible impacts to surface water conditions? And then additional objective of this model was to evaluate the potential for managed aquifer recharge, or MAR, as a potential for supporting increased water use. So in this case, MAR, I'm showing some retention ponds for the Inkster aquifer. So these are recharge ponds that recharge the water table. And the Inkster aquifer is just east of the Elk Valley aquifer in North Dakota. It's a much smaller footprint, but very similar alluvial aquifer. And these recharge ponds have been quite successful at recharging the water table. And so this is an option to include in the Elk Valley aquifer as well. So we built a 2-layer model. Layer 1 represents a clay layer that exists in some places over the aquifer. And then layer 2 represents just the main thickness of the aquifer itself. We have a pretty significant transient history matching period. So from 1970 to 2023, we're trying to match observed water levels. We have annual stress periods from 1970 to 2000 to really capture that wet and dry year trend. And then post-2000, we moved to monthly stress periods. So now we're not just trying to capture the wet and dry year trend, but also the seasonality across the year. And then we have a predictive period as part of our model. That's a 20-year span with monthly stress periods as well. We're simulating aerial recharge using the recharge package and then using the drain and the river package to represent the surface water conditions. And then we're using the well package to represent existing water use. To calibrate this model, we took an ensemble-based calibration approach because we knew we did want to do some uncertainty analysis with this model. So we calibrated to hydraulic conductivity, specific storage, and specific yield using pilot points. So pilot points mean that we include heterogeneity in the solution. And then for boundary conditions, we're also calibrating to the recharge, the drain, and river boundary conditions. We also included the well package because we acknowledge that there is some uncertainty in the water use data. So we allowed that to also vary as a parameter in our calibration. We started off with 480 ensemble members in our prior. In our posterior, we ended up with about 360, and then we used 280 of those for our uncertainty estimation. I'm showing over here is a plot of the total runs, so total model runs versus the log of the objective function. And you can see it over each iteration of our calibration. You can see the objective function is reducing across the entire ensemble. That's those gray lines. And then additionally, that base posterior model, which is essentially your best pick from the ensemble stack if you wanted to move forward with just one model. And in this case, we actually use our base posterior model for our optimization analysis. So that's really a model we're focusing on. The ensemble stack does come into play later, though, when we talk about reliability. These are our calibration results. So on the left here, we're looking at an observed versus simulated groundwater level plot. I'm showing all of the observations in time and space. So you can get an idea, it's colored by depth to water table, so you can get an idea how good our calibration is fitting everywhere throughout time and space in the model. Generally following along those one-to-one line pretty well. And then I've got a transient plot on the right here. It's a hydrograph for one of the locations in the center of the model. You can see each one of those gray points is an observation location. So we have quite a few across the entire aquifer domain. And I'm showing this location, which has data across our entire historical matching, or entire history matching period. So those red dots represent the observations that we're trying to match. And so you can see prior to 2000, that base posterior model is that gold line. So we're really hitting those wet and dry year trends pretty well. And then once we get into the monthly stress period portion, we are catching that seasonality across the years as well. The blue lines represent the entire ensemble, which is spread across the entire data range, as well as the potential noise of the data. So really, really happy with this calibration, a really well calibrated model. All right, so now as promised, I'm going to spend most of the talk here focusing on optimization. So to give a general introduction into optimization problems. So optimization problems exist for every industry and probably every one of you listening on a personal basis. You probably don't realize how often you're trying to optimize the decisions you make on a day-to-day basis. They're composed of these three components. So decision variables, competing objectives, and constraints. So for each one of these, I have an example for like a general processing plant. You could picture like a chair production facility. And then I'm also giving what these mean for our problem in Elk Valley. So decision variables, these are the choices we can control. So for like a general production facility, or say like chair production, these are material grade. Are the chairs going to be made of plastic or wood? Processing time, how much time are we going to spend on each chair? And inspection level, how much time are we going to spend making sure that these chairs are safe and high quality? In our case at Elk Valley, our decision variables are which deferred permits to activate and where to apply managed aquifer recharge. And then competing objectives. So these are the trade-offs that we balance. So a really common example that I have for this general example is minimizing costs and maximizing quality. I think we all have encountered this at some point in our life, that these two things tend to trade off with one another. And so in this case, at this production facility, we're producing chairs. We're really trying to produce the highest quality chairs we can for the absolute minimum cost. In this case at Elk Valley, we're trying to maximize the economic benefit, right? There's some dollar amount tied to this water to be withdrawn that's being requested. But at the same time, minimize environmental impact. We don't want to be impacting any prior appropriators or new appropriators. And we also don't want to be drying up any of the rivers or anything like that. And then constraints. So these are limits we must respect, that, we only want to see solutions that respect these constraints. So for example, safety standards, you can't work every chair production employee until they die. Budget, you only have so much money you can spend on producing these chairs. And then capacity, there's only so many hours in a day. There's only so many people you can employ. There's only so much material you can buy. In this case, for Elk Valley, we're constrained by the installation costs for these managed aquifer recharge basins. We could apply an infinite volume of water across the entire aquifer and get all of the deferred permits activated, but that would obviously be infeasible. We can only install them in certain locations and only can afford to install so many. So all of these components get wrapped up into functions, and we ultimately optimize them using multi-objective evolutionary algorithm. What you end up with is this thing called a Pareto curve, also known as a Pareto front or Pareto trade-off curve, or a feasible front. And so I'm showing a Pareto curve here for our two trading off objectives from my general example. We've got increasing quality on the x-axis and then increasing cost on the y-axis. And that feasible region, that gray boundary, there's solutions all throughout there that meet our constraints. You can picture that top hard boundary line. That's, the maximum, that's the budget. That's the maximum cost we can spend. There's no point in looking at solutions outside of that. And then the curve itself defines the boundary of the feasible solution space. And so every one of those points along that Pareto curve represents an optimal solution. And so it's up to us to pick one of those optimal solutions. So I have a quote here from Thomas Sowell that there are no solutions, there are only trade-offs. I don't know if he was talking about optimization when he said that, but it fits really well, because even though we have this algorithm that's finding the optimal solutions for us, it still is generating multiple optimal solutions, and we still have to sort of pick where we want to trade off our objectives. So in this case, if you look at the lower left-hand corner, our first solution there has really low cost, but also really low quality. And as you move along the curve, you get at the next solution a much bigger increase in quality for just a small increase in cost. And as you work along the curve, there's a knee, and now there's diminishing returns, where suddenly each increase in quality is now costing a lot more. You're getting a large increase in cost. So a reasonable solution that you would probably pick would be just before that curve really starts and you start to get those diminishing returns. So now to apply this sort of idea to our site. So our decision variables are well activation. So each one of those PODs associated with the 49 deferred permits has wells associated with it. However, many are needed or proposed. There might be existing wells, because this might be an existing user requesting more water. So there's over 100 deferred permit pumping wells that we're simulating in the model. Essentially, they can be active or inactive in a solution, any number or combination of them. So if it's active, it's on and pumping at its full requested rate. If it's inactive, it's not pumping anything, it's off. And then we have 4 objectives. So we have 2 objectives for maximizing that economic impact and 2 objectives for minimizing our environmental impact. So our 2 objectives related to that economic impact are, 1, maximize the number of deferred permits active. So trying to maximize the total number of these deferred permit wells that are pumping. And then our second objective is to maximize the weighted permit score. So as I mentioned earlier, that these permits are prioritized by date that they come in, and specifically by their management zone. And so we can take these dates and we turn them into weights. And then in each of the solutions, we can sum the weights across all of the active deferred permit wells and get a total score. And then we're trying to maximize that value. So not only are we trying to get as many of these deferred permit pumping wells active as possible, we're also trying to make sure they're the higher priority wells. Then for our environmental impact objectives, so number 3, we're trying to minimize impact to existing users. So I call this our AFR objective function. AFR stands for auto flow reduce. It's a setting that you can turn on in the well package. The idea being that you can set a threshold, say, a 1/10 of a foot within the bottom of the grid cell. The simulated heads are coming close to that threshold or going to be below that threshold, then it triggers AFR, and that can reduce the flow into that well. And so we're using this AFR triggering as a proxy to impact to existing users or new users. Essentially, that if AFR is being triggered at any point and any time throughout the entire predictive model period, then that is a sign that somebody is not able to acquire the water that they're requesting. So the idea is that we take this auto flow reduce volume from a stress period, we sum it across all our stress periods, we just get a total AFR triggering value. We're trying to minimize that. So the actual number on the AFR is kind of meaningless. It's kind of like an objective function that we're just trying to minimize. And then our 4th objective is minimizing river inflow increase. So there's some baseline amount of river flux going from the river boundary condition into the model. And so any increase in that relative to baseline is seen as essentially this additional volume being pumped from the aquifer is being supplied but partially by this river boundary condition. So by trying to minimize that river inflow increase, we're trying to avoid solutions where essentially we're just drawing on that river package to supply the water. So how that ends up looking in our solution. So what I showed before, a single Pareto curve for 2 objectives that trade off. We now have 4 objectives that are trading off with one another. So I get this 4x4 Pareto curve plot. So each one of these plots represents, one of those objectives trading off with another one. So if you just focus on the top row, the first panel, this is the number of active deferred permit pumping wells versus, again, the number of active deferred permit pumping wells. So you can see there's just a histogram shown there to just show the distribution of the number of active that in this current solution set. And then the next panel shows the comparison between the number of active deferred permit pumping wells versus the weighted metric, that weighted score. So not a whole lot going on in this first generation. And then we see in the third panel, we're comparing between the number of active deferred permit pumping wells and our first sort of trade-off objective, which is the existing impacts, that AFR objective function. So we can see already in this first generation, we're starting to see we've got some AFR triggering going on in our solutions. And then the fourth panel, this represents the number of deferred permits versus the river flux, increased river flux. So again, we're also seeing some increase in the river flux as well. So this is an evolutionary algorithm. So we run this for 150 generations, and each generation, we gain some more children essentially from the previous generation. So we're getting some more model runs with more different activation of different permits and really learning from that and selecting solutions that are pushing towards our optimal solution. So you can see generation 1, and we get to generation 2. Now we're really starting to see those Pareto curves show up in some of these plots. And then I'm just gonna skip ahead here to generation 150, where now you can really see the full evolution of that Pareto curve, particularly in that third panel on the top where we're trading off between the deferred permits and the existing impact. You can see the feasible solution space and then the boundary of that being the Pareto curve. And by the time we get to solution 150, we actually have a decent amount of our solutions that have no AFR triggering. And so that's what's of interest to us, these solutions that have some deferred permits active but are not triggering AFR at all. One important thing to note is that each point on this curve represents a unique combination of active deferred pumping wells. So if you're comparing a solution that has 28 active deferred pumping wells to one with 29, you might think that the 29th solution is just 28 plus 1, but it's not. It's a total different combination of deferred permit pumping wells, which makes selecting a solution kind of difficult. So here are a few solutions that we looked at. So I'm showing 2 with a star and a square, so you can see where they lie on each one of these Pareto curves. Particularly, we were interested in solutions that had no triggering of AFR across that 20-year planning horizon. And we were looking at small increases in river flux, but we were generally finding that as a trade-off, you couldn't really get no river flux increase in this solution. So we selected one that had a small increase in river flux. It ended up having 28 active deferred permit pumping wells. Again, that's just the wells, not the deferred permits that are active. And at a total weighted score of 17.62. So what that ends up looking like. So I'm showing here again the aquifer boundary, and we've got those same POD polygons shown. Anything that's gray is basically a permit that's not activated. Blue, these are PODs that are fully active, but they're part of a permit that has more PODs associated with it that are inactive. So in this case, it represents partial permit activation. And then anything that's not blue or gray represents a permit that is fully active. So in this case, we ended up with 5 fully active permits, no AFR triggering across the 20-year planning horizon, and just these minimal impacts to the river flux. And so this was a pretty good result. This said to us that actually this aquifer could probably support more additional appropriation. And we actually now have some idea of where we can support more appropriation, and that we can do that without potentially triggering any AFR or what we're using as a proxy to impact. So now the question is, how can managed aquifer recharge support this? And so we wanted to test if managed aquifer recharge could push our maximum objectives even higher and our minimum objectives even lower. So in order to test that, we set up the exact same problem, same objectives 1 through 4. But we included a new decision variable. So now in addition to well activation, we can have MAR activation. So we started with these 30 candidate MAR sites. The only really requirement for setting up these MAR sites was they had to be within a few cells of one of these deferred permit pumping wells, and they couldn't overlap with another existing boundary condition. So we set up 30 candidate locations, and we set a constraint that no solutions should have more than 5 in any one of them. So again, just constraining that we've got these candidate locations. Now we're kind of letting the optimizer select the 5 best locations that could maximize our deferred permit pumping activation while also minimizing our environmental impact. And so what that ends up looking like in our Pareto curves. So this is that same 4x4 panel, but we're now showing both the Pareto curve without managed aquifer recharge and with managed aquifer recharge. So if I again focus in on this one Pareto curve where we're trading off between the deferred permit well count and the AFR objective function increase, if you compare between the blue and the gray series, you actually see there's been an entire shift in the Pareto curve, and it's shifted up, meaning we're getting more active deferred pumping wells in our solutions. So just to point out again that now with our blue Pareto curve series here, each one of those points represents a unique combination of deferred permit pumping wells, but also a unique combination of MAR locations. So now we picked a few solutions to look at. So again, showing a star and a square, just 2 solutions that we were primarily looking again at having no AFR triggering. But now in these solutions, we actually do have some that have no river influx increase as well. So our 2 minimum objectives, the objectives we're trying to minimize, were actually pushed to their absolute minimum. And we have deferred permit wells active. So actually in that blue square solution, we have no increase, we have no triggering of the AFR in the 20-year planning horizon, no increase in the river flux over that 20-year planning horizon. We have 43 active deferred permit pumping wells and a weighted score of 26.14. That's compared to the 28 active deferred permit pumping wells we had with no MAR and a weighted score of 17.62. We ended up picking a solution, though, that was a little bit more apples to apples with our impacts from our non-MAR solution, where we do still have that 0 triggering of AFR in the 20-year planning horizon, but we do have about a 2% increase in river flux. That's compared to the 2.5 we saw without MAR. And this had 52 deferred permit well counts and a weighted score of 34.7. So quite an increase in pumping. So this is what those results end up looking like. So again, same plot. We've got blue represents that partial activation, gray is inactive, and then anything not blue or gray is a fully active permit. And now those red circles are representing these optimal MAR locations for this scenario. And so we have 11 fully active permits, essentially with no trigger, no AFR triggering across that entire 20-year planning horizon and minimal impacts to the river flux. So MAR did have a really big impact on this solution, and we were actually able to find, the optimizer really found 5 MAR locations that could really support more deferred permit activation while still maintaining a minimal impact on the environmental conditions. So now the question is, how reliable is that solution? So as I mentioned earlier, we took an ensemble-based approach. So we've got an ensemble stack with about 280 ensemble members. Each one of those ensemble members has its own heterogeneity, has its own hydraulic conductivity values, specific storage, boundary conditions are different in each one of those ensemble members. They all meet similar calibration criteria, but they're all very different in their parameters. So the question is, what if we take these scenarios? We've got 2 different deferred permit pumping scenarios, one with MAR, one without MAR. What if we simulate that across the entire ensemble stack? What does our AFR triggering look like then? And what does the river influx objective look like as well? So this is what comes out of that. So I'm showing a histogram from the entire ensemble. We can see the river inflow increase as a percentage relative to baseline, showing that base model, that 2.5% for the non-MAR scenario, and the gold or the orange line, and then showing the median value with a dashed blue line. And then we've got the 10th to 90th percentile shown with that light blue box. And so what we're seeing is in the 10th to 90th percentile, river inflow increase could range between 1.5 and 3.8%. So still pretty low, pretty close to that base model, even though our base model is on the lower end, a little bit less than the median, but pretty reliable when it comes to the river flux objective. Now, when it comes to AFR, we're seeing the majority of our ensemble members are in that first bin, That first bin does include both 0 AFR triggering and some AFR triggering. But generally, most of them are falling in that first bin. So it's very small, whatever AFR triggering is going on in those ensemble numbers that have it occurring. So when you just look at the number of realizations that have no AFR triggering, it's 115 out of 280. So about 40% of the ensemble members have no AFR triggering, but that means that 60% have some, albeit small. When we look at these same results with our MAR scenario, we see really similar river impacts, 1.5 to 3.5% range. But now when we look at the AFR triggering, we have much less of those ensemble members in that first bin, and they're now more spread across those lower bins. We're still on the low end of the histogram. We're still in the part where that's preferring a much smaller AFR triggering value. Now we see 102 out of 280 realizations had some AFR, or I'm sorry, had no AFR triggering. So that's about 35%. So that means 65% of them have some AFR triggering. So with this AFR objective function, as I mentioned, it's kind of meaningless. We don't really understand what the actual value means. So in order to get a picture of what that value means, I look at it as a ratio of the amount of the AFR triggering compared to the total requested volume. So in the case of no MAR, if we look at this as a percentage of the total requested pumping, our 10th and 90th percentile range shows 0 to 4%. So what that means is essentially 90% of the realizations have an AFR increase less than 4% of the total requested pumping. So that's pretty reliable. That's a pretty small amount. It's probably within an error margin of how we are representing these pumping wells in general. Additionally, there's uncertainty related to the total requested rate. There may be less in some stress periods than we're actually simulating. So again, 4% is pretty low. We find that to be a pretty reliable solution. But now when we look over at the MAR scenario, we see the 10th to 90th percentile shows a range of 0 to 17%. So that means that 90% of the realizations have an AFR increase less than 17% of the total requested pumping. So now our upper end of our 90th percentile is looking at almost 1/5 of the total requested pumping. So not as reliable. We're still on the low end. Our median value is 2.6% of total requested pumping. So it's still pretty low, but not as reliable as the non-MAR scenario. And if you think about it, this makes sense because we have more than about double the pumping in the MAR scenario. And essentially the optimizer found these locations for MAR retention ponds that optimized and got more deferred permit pumping. But now when you look across the entire ensemble stack, it shows that those MAR locations are not as effective as they were in the base model. So it makes sense with that additional pumping and then now looking at different heterogeneities, different combinations of parameters, we don't see as reliable of a result when it comes to this AFR triggering. So where we would take this reliability in the next steps, and ultimately what we plan to do. So let's say, we're pretty happy with the no MAR scenario and its reliability, but let's say, we really are thinking of moving forward with these MAR locations and we want to get the MAR locations even better than they are. So we want to get that reliability higher. So we know that greater than 50% of the realizations trigger some AFR. So maybe we want to get that improved. So what we can do is run this optimization algorithm across the entire ensemble stack and add a reliability requirement. Say we want greater than or equal to 70% of the realizations to have no AFR triggering across that 20-year planning horizon. So that would be including it as a constraint, saying that I only want to see solutions where 70% of the ensembles show no AFR triggering. We could also formulate it as an objective. Say a 5th objective, just maximize reliability, push it towards 1 if you can. Let's see 100% of the realizations have no AFR triggering. That might be too much, but by including it as an objective, you can see that trade-off. Another option is you can include it as an objective where you're trying to minimize the value that 70% of all the realizations fall at or below. So maybe that's not going to be, 70% of the realizations falling at 0, but maybe you could get it down to 1% of the total requested pumping. You can minimize that value. So the idea being really here that as a constraint, you're looking for the cheapest solution that meets a reliability bar. But let's say, that solution really has not that many deferred permits active, and you're just wondering, well, what am I trading off here with the reliability? So then you included an objective and you can get that full trade-off picture. Now you can see, okay, if I have even just a few more permits active, my reliability is down at 65%, which to me is a fair reliability and I'm okay to move forward with. So it really just depends on your decision and what you're trying, choice you're trying to make related to the reliability. Now, the main drawback with this is that it's many, many, many model runs. To give sort of a picture of running just this initial optimization problem on the base model, each one of those generations, you're running the model hundreds of times. Our model, had a lot of decision variables, and so you do have to run the model quite a bit to get a full picture in each one of those generations. Our model only took about 10 minutes to run, sometimes longer, sometimes shorter, depending how many of these deferred permits were active. And we had 200 computer processors that we could parallel process across to run this algorithm. And it still took about 12 hours, which is really not that bad. I figure you can run that a few times and iterate on it and get a solution. But now imagine for each of those generations where you're running the model hundreds of times, each of those models represents 280 models. And so you're multiplying everything by 280 basically. So that's where I'm saying, now you've got weeks of model runs, potentially months of model runs, depending on your computation processing power. So a potential solution to that would be emulation. I have here that that's a story for another webinar because an entire webinar could be focused on model emulation. But just to give you sort of a brief picture into what I mean by that. So this would be using a response matrix emulator, essentially a model of a model, which just understands the way the system responds to certain stresses and emulates the simulated results, all based on the principle of superposition. So it's just a model of a model. So where your model might take 10 minutes to run, this emulation or emulator of the model takes, a fraction of a second. And so you could take these potential weeks or months of model runs and boil it down into hours or, maybe a day or something like that. But it makes it much more realistic for someone to include reliability as an objective, especially if they don't have 200, computers to run parallel on like I did. Right, so that's the majority of my talk here. I'm just going to spend a little time here talking about considerations of this optimization problem, and then I'll summarize, and then I'll show what we plan to do in the future. So important considerations. Problem formulation is an iterative process. Anyone on this call who's built groundwater models, that that's an iterative process to calibrate them, where you're going back and forth to the drawing board, you're rebuilding the model, you're changing the scope of things, you're changing your parameter bounds, et cetera. It's an iterative process. It takes a long time. This is true with optimization as well. I'm showing what we landed on with our optimization objectives and our constraints, but we went back and forth on this and had many different combinations that we tried, results that didn't really make sense, things that were too restrictive, et cetera. So we finally, it took a long time to end up where we did. And so problem formulation is really important, just like it is with calibration. There are many objective and constraint possibilities. So I'm showing a few here on the right. I'm talking about economic incentive. So you could attach a dollar amount to each of these permits, and you could try to maximize the dollar amount. You could try to minimize maximum drawdown across that 20-year planning horizon. Or you could also add, say, a stabilization of the hydraulic head criteria. I bring these last two up, and I'm showing, two thoughts from our scenarios. So I've got here hydrograph on the left. So looking at the entire historical period and then that predicted period once you get past 2023. So I'm showing our base model versus our scenario 1 optimization model and our scenario 2 optimization model, which includes MAR. You can see both have drawdown relative to the base model, about 3 feet, not too much, but you can see that it's maybe not quite stable at the end of that 20-year planning horizon. And so you could add in a requirement where, say, the change in water level for like the last 4 stress periods can't be more than X feet or something like that. And so you're trying to select solutions that have stabilization towards the end of your planning horizon. I'm also showing a plan view of the maximum drawdown. So this is from the beginning of the predicted period to the end of the predicted period. You can see both of our solutions, we have drawdown near 20 feet near the wells, maybe like 8 feet away from the wells. Some states actually have an actual linear measurement requirement that no additional permit can draw down the water table more than X amount at a certain distance. And so that can be included as a constraint as well. I don't want to see any solutions with, say, draw down more than 8 feet or something like that. So again, just there are so many possibilities of ways you could set up this problem and get the results that you're looking for. So to summarize, optimization problems can be applied to groundwater models to help with regulator management. Ultimately, this problem is sort of in the beginning stages. It's not meant to necessarily be taken these results and just run and activate these permits. But the fact that we do see in our non-MAR solution that there are some permits active with no AFR triggering is a good sign. That to us gives some confidence both in the decision maker and the modeler that this aquifer can support additional appropriation. So you can start sort of moving forward in that process. The setup of the optimization problem is crucial to getting reasonable results that satisfy objectives and constraints. So again, going back to that problem formulation, it's really important to get that right. And it's an iterative process. And these results demonstrate general regions where MAR may be beneficial to increasing water use. But as you saw, if we really want to nail down where those MAR locations are best, we might want to rerun this with reliability included. So our plan is to further refine our objectives and constraints, as well as the MAR locations, and then ultimately include reliability as an objective. All right, and that's the majority of my talk. So just want to, again, give a special thanks to the North Dakota Department of Water Resources. They're asking these tough questions and really interested in using really cool scientific ways to answer them. Jeremy White, who developed most of the tools that I used here today to present these results, and then Ryan Harmon, who was our technical lead on this project and was a really important piece in making sure that this model was developed correctly. And so big thanks to him as well. But with that, I'm sure we got some questions. See, Jeremy, you're back. I don't know if you got any questions or anything you want to share with me. Okay.
For sure. Excellent talk.
Thanks.
That was amazing. Okay.
Thanks.
So someone asked, do we include future weather or climate change scenarios into consideration?
That's a great question. So not for the optimization. For the optimization, we're just running it on what we call our base predictive model, which is essentially assuming things are status quo going into the future. We do have a drought scenario that we looked at just to understand how drought could impact existing conditions, but we didn't do any analysis with the optimization with the drought scenario. So that could be something too to consider as both impacts of climate change, but also worst case conditions, with these additional deferred permit pumping wells. What does that look like under drought conditions?
Someone is asking, when selecting the MAR locations, were hydraulic conductivity and gradient considered or not?
Not for these MAR locations. They were just sort of randomized throughout the domain, just trying to get within the deferred permit pumping wells within that area. But that would be something to take the next step to really understand, where could we put them based on, say, property ownership or, distance to the water table, things like that for ease of construction. But for this first initial step, they were randomized and just focused on supporting more water use.
And yes, there will be a recording later. Do we have any other questions or comments from Mel? That's a really good question. Do you see that question?
Yeah.
You need to read it, Mel.
Yeah, I'll read
You
it.
got it?
So how fast does a model run have to be to reasonably consider evolutionary algorithms as a method of optimization? Most literature mentioned that speed is important. Is this also true for this method? Yeah, we specifically designed this model to run quickly. It was a goal we had in mind for the model from the beginning. I didn't list it as an objective, but the first objective is that it has to run quickly. And so that was really important to setting up the model to do that. So if you have a model that you want to do this on that already takes, say, hours to run, I would prioritize getting it to run quicker before potentially running multi-objective evolutionary algorithm on it.
Yeah, I think I would even add it's a constraint, not even an objective. Like you got to have a fast model where this isn't going to work.
Yes. Yeah. Fast and maybe stable too. I mean, this was a pretty stable model. So especially when you're starting to simulate that additional deferred permit pumping, if it's unstable, you're going to start getting convergence issues and slowing down. I see a question. What codes were used for this? We used PES++, MOU, it's called. It stands for multi-objective uncertainty, I think, something like that. Jeremy, you made it.
Yeah, that's it. That's right.
And then, is it possible to simulate river diversion during heavy rain as the MAR source? So you could, we based our MAR flow rates on the existing retention ponds in the Inkster aquifer. But if you did say have an actual source for that, say like a routing source, I don't see why not, if that's included in your model, that you could use that as a source. And then, yeah, I guess you could base it on, say, it could link up with your temporal structure of your recharge. If you have higher recharge periods, then you could divert more water to the MAR ponds, et cetera. You could definitely make the problem more complicated in that sense, I would say. In-season benefits for MAR locations. So the impacts of MAR are seen during the irrigation season versus out of season. Yeah, so same answer to that question. You could make it seasonal. I actually think the MAR that we're simulating is seasonal. We were having it only active during the summer months. So it was actually feasible instead of constant MAR representation. Oh, Dr. Markovich, we know her. She used cost of marls, et cetera. As far as I understood, you didn't consider cost. No, did not consider cost. Yes, just considered river inflow. Correct. Yep, did not consider cost at all. It just number of locations to sort of as a proxy to, we couldn't have too many because it would be too costly. The prior appropriation, so we just had how prior appropriation was considered. We just had the baseline scenario, which was kind of representing existing appropriation, existing water use. And then that essentially was just averaged, on a monthly seasonal average basis for the entire 20-year period. So assuming just prior appropriation will be the same for that 20 years. Okay. Were streamflow data included in the calibration data set? Not included in the calibration, but we did use streamflow data as sort of a benchmark to make sure that our flow rates were not the flow in the actual package, but the flow from the surface water boundary condition into the model was reasonable and not too high, say. Were the wells pumping continuously or time dependent? They were time dependent. So they were following an irrigation schedule mostly. If they were irrigation wells, if they're, say, rural water wells or municipal water wells, then they were constant source. How many model wells were required for the conversion? Model runs, sorry. Many. How many did we specify per generation, Jeremy? It was related to our decision variables, right?
Yeah, so it was twice the number of decision variables.
So yeah, there was at least like it was over 100 decision variables. So picture like at least 200 model runs per generation. We ran 150 generations. So quite a lot.
Yeah. So 15,000, 20,000 model runs.
Yeah. Sorry if I missed this detail, but did you perform the optimization on the same model that you calibrated, or did you take the calibration parameters from the posterior and load them into a forecast model? Good question. It's the same model that we calibrated, and the forecast period is based on the calibrated stresses. So calibrated recharge is just, again, we took some average recharge value from the previous 5 years, applied that to our predicted period, average pumping well calibrated data, applied that to our forecast period, and all the parameters represent the calibrated values from both the ensemble data set and the base model where we were applying those predictive analyses. And load them. Yeah, no, so we didn't just run the forecast model. The whole model was ran every time. So that is something that you could potentially do to make it quicker, is potentially build just a forecast model. Water user specific impacts. The objectives appear to be largely utilitarian. Mm-hmm. Yeah, that is a good point. Our objectives are pretty simple. And we're not looking at specifically who was being triggered, had AFR triggering going on. And that could be boiled into your objective problem as well. Say if there are certain, we had a weighting score for prioritizing permits. And if there's certain permits that really can't afford to have, like these have to get the water they need, for instance, but maybe say other permits are not as big of a concern, potentially, you could include that in your solution. In this case, the goal was just to get no AFR triggering, but we just included it as an objective up front just to see where we were balancing that trade-off. How would I present this to non-expert decision makers? I don't know. Good question. Are there plans to incorporate additional information impacts to model calibration? How that translates to potential uncertainty? If you added a few more monitoring wells at key. Okay, I got you. Yeah, go ahead, Jeremy.
I was gonna say that's that data worth question. Yeah.
Yeah.
That data worth thing we were just talking about, like that if you collected some data, recalibrated, had less uncertainty, maybe you could find more reliable solutions that still, maybe included more with a higher degree of reliability. But again, you have to propagate that through the optimization, which is costly.
Yeah. We didn't, I think, specifically look at that question of where to add key locations, but we looked at more where there were redundant locations when we looked at data worth. Okay. That was pretty much the last question. Just more thank you. Okay. Well, I don't know if we hang on here or wait for more questions to come in.
I think we've done pretty well, Mel.
Okay. All right. Well, really great questions.
Thanks again, everyone. Yeah. Oh, go ahead, Mel.
That was it. That was just
you want me to
really great questions. Thanks for the contribution. And yeah, you can go ahead and close it out.
Yeah. So thanks everyone for coming to the webinar. We appreciate all the discussion here at the end, especially, and we will get that presentation recording sent out today to everyone who signed up, even if you didn't attend. So everybody's going to get a link to that, hopefully by the end of the day today. And with that, I think we'll sign off. Thanks again, everyone.
Thank you.